Great. So I will continue from where we left off. Yesterday, I gave a very broad brush introduction to the Swampland. Several conjectures were introduced. Among them is the weak gravity conjecture. And so in the lecture today, I will present a simple proof of a mild form of the weak gravity conjecture using unitarity and causality. Now recall that the weak gravity conjecture states that gravity is the weakest force. More precisely, for every long-range force in the theory, the conjecture postulates that there must exist a state whose charge-to-mass ratio is bigger than 1, or more precisely, the charge-to-mass ratio of an extremal black hole. So this is oftentimes known as the mild form of the weak gravity conjecture, because we only require the existence of some state without putting any additional conditions on what that state might be. Now, I gave some motivations for the weak gravity conjecture. The motivation for the weak gravity conjecture is for an extremal black hole to decay. Now, unlike the no global symmetry conjecture, it is not clear why an extremal black hole needs to decay, so it's not clear why the weak gravity conjecture should hold, although there are evidence of the weak gravity conjecture from various different fronts, based on examples or based on consistencies that, like consistencies among point-Kaluza-Klein reduction, consistencies with holography, and so on. So there have been tests of the conjecture, although there's no sharp statement that have been made about why this conjecture should hold. Okay? So the picture to keep in mind is, if the weak gravity conjecture holds, an extremal black hole whose charge is equal to the mass in the classical sense, it should be able to find a decay channel, and the existence of a super extremal state is what makes this possible. Okay? Now, I also mentioned that several stronger versions of the weak gravity conjecture have been proposed. For instance, now you could require this state that satisfies the conjecture to be a state in the low energy effective theory, which was not originally required by the simplest form of the conjecture. So there have been also stronger forms that require the state that satisfy the conjecture to be the lightest charged particle in the spectrum. That has proven to be wrong. And there have been conjectures, stronger form of the weak gravity conjecture that requires infinitely many charged states. And those charged states satisfy the inequality that I was showing in the previous slide. And it goes under the name of the sublattice weak gravity conjecture, which we reviewed last time. It was motivated from either holographic argument or through a worldsheet argument. So if you look at perturbative string theory, if you look at the worldsheet that describes the partition function, you can use spectral flow to argue the existence of a state that satisfies the weak gravity bound for a sublattice of the full charge lattice. Okay? And in the lecture today, we will see another strong form of the weak gravity conjecture known as the tower weak gravity conjecture. It is very similar in nature. It also requires infinitely many charge states satisfying this bound, except that the infinitely many charge states do not need to fill even a sublattice of the charge lattice. So we can think of the tower weak gravity conjecture as a slightly weaker form of the sublattice weak gravity conjecture that we talked about before. Now, so far, we haven't found any counterexample to either of them. It remains to be seen whether such strong form holds in general. Okay? So the plan for today's lecture is to first present a proof for the mild form of the weak gravity conjecture, namely to find a decay channel for an extremal black hole using arguments based on unitarity and causality. And after that, we will present some evidence for a stronger version of the weak gravity conjecture that we call the tower weak gravity conjecture. So roughly, this is the plan for today. Now, recall that the original conjecture was motivated by black hole physics, namely the requirement of the weak gravity conjecture is for an extremal black hole to find a decay channel. So the mildest form of the weak gravity conjecture requires only some state, some decay channel for this black hole. A very natural question is whether a smaller extremal black hole can serve the purpose. So whether a large extremal black hole can decay to a smaller one. And if we can show that, then it would be a proof of the mild form of the weak gravity conjecture. And the reason why this is not completely crazy is that what we mean by an extremal black hole is subjected to quantum corrections. So when we say a black hole is extremal when its charge is equal to its mass, this is a classical statement. It is subjected to quantum corrections, including loop corrections or higher derivative corrections. In particular, the higher derivative corrections to, say, the simplest Einstein-Maxwell theory would correct the black hole solutions, and as a result, the extremal conditions. So you would expect the corrections from higher derivative terms to be very small, unimportant for an extremely large black hole. So if you crank up the mass of the charge, the extremal black hole should lie along this straight line. But this is not the case when you look at smaller and smaller black holes. When the black holes become smaller, the higher derivative corrections are not so insignificant. As you will see, the higher derivative corrections are suppressed by the mass of the black hole. For smaller black holes, they are not negligible. And so could smaller extremal black hole, can we show that the smaller extremal black holes lie on a curve like A, where they are super extremal in the classical sense? And if that's the case, that would provide the decay channel for the large black holes. And this a priori seems promising because back around the time when the weak gravity conjecture paper was first written, shortly afterwards, Motto and collaborators demonstrate that the higher derivative corrections to some four-dimensional black holes in string theory would make the extremal black holes lighter than the classical bounds. In particular, they were looking at some heterotic string black hole solutions, and they compute the higher derivative corrections, and they find that, indeed, the black holes, the extremal black holes, including the higher derivative corrections, would lie on a curve like A, and not the other way around. If it had been the other way around, then it would not be a candidate for the weak gravity state. So what we show, and I will explain in this lecture today, is that this behavior actually follows from some very basic principles, namely unitarity and causality. Well, with some caveat. We cannot show it in general, but at least for a wide class of theories, which, as you will see, can be naturally realized in string theory. So not every theories we would not be able to prove for every theories, including the higher derivative corrections would allow the extremal black holes to lie on a curve like this, but at least we can explain this behavior for a wide class of theories that are not completely disconnected to what we know about low energy effective theory of string theories. Okay, so first, before we go over the proof, let's just be a bit more precise about the extent to which this proof would apply. So we will have to make some assumptions. We would assume that we have a weakly coupled UV completion. So there will be some energy scale, some high energy scale that I call lambda QFT, beyond which the ordinary quantum field theory description breaks down. So this is quite reasonable. In string theory, this would be the string scale, above which we have infinitely many local fields. Okay? So even if we have a breakdown of the EFT above lambda QFT, in string theory, we know that, in perturbative string theory, we know that at such a scale, lambda QFT, the theory is still weakly coupled. So at the string scale, we don't yet encounter strong gravitational effects. So this would be the context in which our proof would apply. So we would assume that we have a weakly coupled UV completion. Now, within this context, we were able to show that the mild form of the weak gravity conjecture follows for at least two classes of theories that we can identify. Okay? The first class of theories are theories with some light, neutral, parity even scalars below lambda QFT. So in general, you could envision several possibilities. Either all the states are heavy, so there's no like states besides graviton and the photons. Below lambda QFT, there are no like scalar degrees of freedom at all. There would be some situations like on the right-hand side. But for theories that have some like degrees of freedom, parity even degrees of freedom below the lambda QFT scale, this would be a picture like on the left-hand side. And so for theories with light, parity, neutral, parity even scalars, or with fields that have spin bigger than 2 or above, we can show that the mild form of the weak gravity conjecture follows, namely that the higher derivative corrections would always make the charge to mass ratio bigger than 1. Now, light here means lighter compared with the lambda QFT scale. They don't necessarily have to be very light. So they just have to be lighter than what we call lambda QFT or the string scale. Now, even if you don't find any like degrees of freedoms below the scale at which quantum field theory breaks down, the same kind of arguments that we made can be applied to theories, to UV completions, where you have two different sets of higher spin states. And this would be the case, for instance, in open string theory, in theories with open strings. We have different towers of Regge states, one associated with the graviton and one associated with the photons. And if you can find that there are two types of Regge towers, we can apply the same kind of argument, as you will see why this assumption would be necessary. Okay, so let's get started. Let's start from the very infrared and build our theory up. So in the infrared, when we describe the dynamics of an extremal black hole, we can write down an effective field theory describing the dynamics of the photon and the graviton. And if you keep the lowest order, it would be just the usual Einstein-Maxwell-Lagrangian. But we are interested in what the higher derivative corrections can change the black hole solutions and the extremal conditions. So we have to work a little bit harder and include the higher derivative corrections to this effective action. So even though in the infrared the dynamics of the black hole is described by this EFT, they are subject to these higher derivative corrections. And you can convince yourself by doing this operator analysis that in 4 dimensions, the general effective action up to 4 derivative operators are all given here. So these are all the terms you can write down up to 4 derivative levels. It's still rather complicated. There are many terms. But you can use field redefinition using equation of motions to simplify it. So there are only 3 terms to leading order in the derivative expansions that I call alpha 1, alpha 2, and alpha 3. So alpha 1 is f to the 4th term. This is ff dual square term. And then there's a term that involves the wild tensor. Okay? So there are 3 Wilson coefficients that I call alpha 1, alpha 2, and alpha 3. And now, including these higher derivative corrections, obviously, when you solve for black hole solutions, the solutions will be corrected. And the extremal black hole, the charge to mass ratio for an extremal black hole is also corrected due to these higher derivative effects. And we will stay with the lowest order corrections and keep only the leading order higher derivative terms. This will be sufficient if the effect is small. So we are self-consistently looking at the regime where these effects are small and we keep only the leading order effects. This would be the case when the black hole is sufficiently large. This is because the scalar curvature and the kinetic energy that would appear in this expansion, they all scale inversely with the black hole mass. So for a large enough black hole, you can keep only the leading 4 derivative operators. Okay? So if we are living with this very simple context, proving the weak barrier conjecture just amounts to proving an inequality for these Wilson coefficients. And this charge to mass ratio is no longer 1 that applies to the classical case. There are corrections that goes inversely with the charge or the mass of the black hole. But whether this is bigger or smaller than 1 depends on the sign of this combination of the Wilson coefficients. So we will see that for the 2 classes of theories that I mentioned, this weak gravity bound with a strict inequality follows from basic principles such as unitarity and causality. Okay? So the proof is a bit messy and technical. So let me just briefly sketch the argument before we go into the details. Okay? So it goes in at least 2 steps that I could imagine. Okay? So the first step is to show that for the 2 classes of theories that we mentioned, causality implies that there is a hierarchy of the Wilson coefficients. So we will show that for the 2 types of theories that I mentioned, alpha 1 is much, much bigger in magnitude than alpha 3. And the reason is that the higher derivative operators that I label as alpha 3, which include the wild tensor, would generate new photon-graviton helicity amplitude that are not present in the original Einstein-Maxwell theory. And this new helicity amplitude would violate causality at an energy scale that is set by this Wilson coefficients. So above the scale, which is given by m Planck divided by root alpha 3, there's causality violation at an energy scale set by the Wilson coefficients. Moreover, it has been argued that not only do we see causality violation, an infinite tower of higher spin, massive higher spin state, just like string theory, is required to UV complete the effective field theory. So when this happens, you bring in a whole tower of higher spin states. Now, the reason why we make the assumption about the two classes of theory is that when there is a like scalar degrees of freedom, or when there's a different towers of Reggie states, this higher derivative operators which violate causality would be subdominant compared with the causality preserving ones. So we will see more carefully when we do the operator analysis that the existence of these like scalar fields would generate operators that are bigger. And so you can treat alpha 3 as a subdominant effect. Now, the second step of the proof is to show that the f to the fourth coefficient that we call alpha 1 is positive. And this follows from unitarity. And there are probably different ways of seeing this, but to prove the positivity of the f to the fourth term, you can consider the forward limit of the photon scattering amplitude. And you would simplify your life tremendously if you write out this amplitude in a nice basis, which is the so-called spinning polynomial basis. And that makes clear what is the mass, the spin, and the helicity of the intermediate states that are being exchanged in this 4-point amplitude. And so the scattering amplitude of the photon-photon scattering amplitude in the forward limit take this schematic form. There is a whole bunch of sums of poles, okay, together with an analytic term. And you can show that the analytic term is bounded strictly by S squared. This is the usual Froissart bound. And now, considering the effects of the higher derivative operators, the f to the fourth term, it gives rise to a contributions to the scattering amplitude that goes like S squared. So the fact that there isn't any terms that is going as strong as S squared in the analytic piece implies that unitarity would imply that this coefficient alpha 1 has to be positive. So together, combining these two arguments, namely that there's a hierarchy in the magnitude of the Wilson coefficient, and the fact that unitarity implies this f to the fourth term coefficient is positive, implies that the weak gravity bound is satisfied. So pictorially, you can think of it as the following. An extremal black hole, a very large one, where the higher derivative terms are unimportant, is given by Q equals to M. It can split off to a small, it could split off a smaller extremal black hole whose charge is bigger than the mass. And this decay channel, unlike the classical limit, is allowed because of the higher derivative corrections. Okay? So this is roughly the argument. Okay? So the rest of the 2/3 of the lectures in the coming hour would be to just make these statements a little bit more precise. Okay? So let's go through the argument in a little bit more details. Okay? So now you could ask, what are the sources of the higher dimension operators that could induce this black hole decay? And there are several contributions. Okay? So you can generate these higher derivative operators by exchange of the neutral bosons. Okay? So this will be what we call effect A. So there are three types of effects three sources of higher dimensional operators that will contribute to these higher derivative corrections to the effective actions. The first type of contributions come from neutral bosons. Okay? So you can keep in mind that these neutral bosons could be your dilaton or some other moduli that are stabilized below the string scale. Okay? So if the masses are lower than the string scale, that would satisfy the criteria, and they would generate they would generate the type of operators that we want. Now this is a tree-level effect. There are also higher dimensional operators that are generated by charged particles. So instead of neutral particles like the dilaton or some geometrical moduli, there are other heavy degrees of freedom that you could integrate out and generate these higher dimensional effects. And unlike the neutral particles, the charged particles do not contribute at the tree level. The leading contribution is at one loop, and so you can write down the diagrams corresponding to the type of Feynman diagrams that would generate the higher derivative operators by integrating out these heavy fields. There are also contributions coming from integrating out UV physics. By UV physics, I mean physics above lambda QFT, so where ordinary quantum field theory description breaks down. So in string theory, you can think of this effect as coming from integrating out the string states. These are what we call the alpha prime corrections in the low energy effective actions of string theory. Okay? So having in mind that these three different contributions to the higher dimensional operators, we could now discuss the unitarity constraints on each of these contributions. Okay? So let's start with something simple, because this is a tree-level effect. Consider in your theory that in addition to the graviton and the photon, there are some heavy fields. They are massive, but they are below lambda QFT. So depending on whether you have a scalar or a pseudo-scalar, it will generate for you different higher dimensional operators. If you have a theory with a scalar, integrating out this scalar would generate this f to the fourth term, which I call alpha 1. And if you were to integrate out a pseudo-scalar, it would generate, on the other hand, the other term, the term that involves FF dual. Now, you notice that these coefficients are positive, and this is a consequence of unitarity. So more generally, the positivity of these Wilson coefficients from integrating out scalars or pseudo-scalar can be argued using unitarity. And now, again, the proof is not very deep. All you have to do is to express your scattering amplitude in terms of a good basis, like the basis that I have illustrated over here. So you can show that if you have a scalar, a parity even scalar, integrating a parity even scalar would generate for you the type of terms that contributes to f to the fourth. Whereas if you have a pseudo-scalar instead, it would generate for you the term that corresponds to FF dual square. Okay? And so, moreover, by writing out the scattering amplitude in this nice basis, you can show that not only do you generate such a term by integrating a scalar or pseudo-scalars, anytime when you have particles with spin 2 or above, it will generate for you this Wilson coefficients, which are positive definite. Okay? So this is a tree-level effect that you can show rather easily. Now, other effects come from charged particles. So they don't contribute at tree level, and the leading contribution is at one loop. Again, you can write down different diagrams that will contribute to these different high derivative terms. And in particular, if you consider the a minimally coupled charged particles, integrating out this minimally coupled charged particle would generate for you higher dimension operators to the effective actions that goes with different powers of the charge to mass ratio of the particles. So Z here denotes the charge to mass ratio of the particles, depending on how many of them involving the gauge couplings. Here I have a diagrams that generate f to the fourth term with 4 couplings. And so this goes like the charge to mass ratio to the power 4th. And so for the 2 higher derivative corrections that do not involve the wild tensor, they go in different orders of the charge to mass ratio, whereas the higher derivative operators that involve the wild tensor only has terms that contribute to order Z squared. So there are only 2 vertices that involve the gauge coupling, and so the coupling, corresponding coupling goes like Z squared. Okay? So this is a rather boring operator analysis, but it tells you something. It tells you that if you can find a particle in your spectrum whose charge to mass ratio is much, much bigger than 1, like what the weak gravity conjecture suggests, then there's a hierarchy in this Wilson coefficient. So the 2 higher derivative operators that does not involve the wild tensor would be much, much bigger than the one that violate causality, as I mentioned. Also in this limit, things are much easier because gravity, because the gauge coupling is much stronger than gravitational effect. And so unitarity of quantum field theory, usual quantum field theory, would imply that these 2 Wilson coefficients are positive definite. Okay? So you can go through the unitarity argument just like before for the tree-level effect, but even for loops, you can show that these 2 Wilson coefficients have to be positive definite. Now, that means the following. So if you can find particles in the spectrum whose charge-to-mass ratio satisfy the weak gravity bound, not only do you satisfy the weak gravity conjecture with that particle, the Wilson coefficients will work in such a way that a large extremal black hole can decay to smaller ones. So you have two types of candidate weak gravity states. One will be just the particles themselves, and the other will be a smaller extremal black hole. So either way, you satisfy the weak gravity conjecture. But that's not a particularly interesting case because you already have a weak gravity satisfying particles in the first place. However, if you go to the opposite limit, when you don't find such a state in your spectrum, when you don't find a state whose charge-to-mass ratio is large, you violate the weak gravity bound with its particles, then there's no vigorous unitarity bound as far as we know. So we don't know whether these Wilson coefficients are comparable or one is bigger than the other. Moreover, unitarity constraints on this Wilson coefficient is not clear. The gravitational effect is not negligible. However, this is also the limit when the other effects that I call neutral boson effects or the UV effects would dominate. So whenever you have the other effects contributing, you don't consider this as a dominant effect. Okay. And finally, perhaps more interestingly, is the contributions coming from integrating our UV physics. And so again, you would expect, just based on general operator arguments, that integrating out this UV physics would generate higher dimensional operators that are suppressed by the high scale. So you can call it lambda QFT or you can call it the string scale. So these operators are suppressed. And depending on how big this operator, how big is the scale of lambda QFT compared with the masses of the other light fields in the spectrum, this could be a subdominant effect. If you find some light particles whose effect will be suppressed by the mass of the particle, this is a much smaller effects in comparison. Okay. Now, in string theory, we know what these UV physics effects are. These are what we call the alpha prime effects. And so in general, it's difficult to say something concrete about the sign of the higher derivative corrections without reference to anything specific about the details of the UV completion. And a crucial obstruction in deriving a unitarity bound for gravitational theories is that if you run the same argument as before, looking at the forward scattering amplitude in the limit when the Mandelstam variable t goes to 0, you find that it's dominated by the tree-level exchange of a graviton. Okay? And so schematically, you can write down the scattering amplitude in this manner. In the forward limit, namely when you take the Mandelstam variable t to 0, it dominates. It's dominated by the tree-level graviton exchange, and it goes quadratically with the Mandelstam variable s to 2 powers. So unlike the previous two cases, this is not strictly bounded by s squared. So that means that we cannot just use unitarity to bound the coefficients of s squared anymore. If the scattering amplitude involves something that is not strictly bounded by s squared, the analytic term would contribute, and in general, they could contribute with a coefficient that is perhaps even negative. But we know that this is not a complete story. And presumably, this UV behavior would be made mild if the graviton is accompanied by a tower of higher spin states, as in string theory. So if you were to write down the string scattering amplitude instead, it doesn't just go like s squared. This just doesn't go quadratically with the square of s. It's accompanied by an infinitely many contributions to all orders in T. Okay? So in string theory, this gamma that I put over here would be the alpha prime scale. Okay? So if you look at this scattering amplitude, including the whole tower of higher spin states, it is bounded by s squared for a small, in the forward limit, as long as this coefficient gamma is positive. Okay? So now if you were to expand the full string amplitude into terms with different orders in T, you may be led to a somewhat discouraging conclusion that the next order term, if you just blindly expand this amplitude to the next order, it is no longer bounded by s squared. It actually goes like s squared log s. And so even though it's polynomially bound, it's less bounded than the non-gravitational case. Okay? But this is just because we are not taking into account the full string amplitude, but only the leading order effects. And so if you were to take this leading effect in the scattering amplitude, the analytic part, since it's only strictly bounded by s cubed, so the analytic part of the scattering amplitude may contain terms that goes like s squared with possibly a negative coefficient. And so you cannot just use unitarity to bound the Wilson coefficients alpha 1, alpha 2, and alpha 3 because there could be contributions from the analytic piece of the scattering amplitude. So let's compare the effects coming from this higher spin states. So we said this UV effects would be suppressed by the scale of lambda QFT, and in string theory, this lambda QFT would be the string scale. So you could estimate the size of these higher derivative terms. It should go like 1 over the square of, it should go like 1 over m string square. Now, if we don't make any further assumptions about the type of theories that we consider, we cannot go any further. But if we could find other contributions to the higher derivative terms that are more dominant than these contributions from the graviton higher spin states, then we could ignore these contributions and focus on the contributions that are dominant. And this is the case, for instance, when you find that there's a light neutral scalar with a mass that is smaller than the string scale. So if there are effects coming from what we call effect A, whose effect is suppressed by 1 over the square of the mass of the particle, and if the mass of the particle is lighter than lambda QFT, then this effects coming from integrating our string states will be subdominant compared with the neutral boson contributions. Okay? So that's the reason why we identify the first class of theories where we have light scalar fields in the low energy spectrum below lambda QFT. Another possibility is if there are different higher spin towers that accompany the photon and the graviton. And this is the case, for instance, in theories that have both open and closed strings. So there's a tower of higher spin states associated with the graviton. These are closed string excitations. There are also higher spin states associated with the photons. These are open string excitations. And since we make the assumptions of weak coupling, UV completion is weakly coupled, the contributions from the open string excitations would be more dominant compared with the closed string excitations. They are, since the coupling is small, the open string coupling is stronger than the closed string coupling. So if you don't find any light particles in your low energy, but you have a different Reggie tower, the contributions from the open string towers would be bigger than the contributions from this closed string tower. Okay. So in other words, in UV completions, where the higher spin states that accompany the graviton are subdominant in the photon scattering, this would be the case where we have some open string Reggie tower. We can again use unitarity to prove that these two Wilson coefficients are positive. Okay? So summarizing the unitarity constraints for the various cases that we study. So we have contributions from neutral bosons. The effects will be suppressed by the mass of the particles. Unitarity, in this case, would imply that each individual Wilson coefficient is positive. And there could be positive contributions from loop effects. And depending on whether the spectrum contains particles with large charge to mass ratio or not, we have two different possibilities. When you have a large charge to mass ratio, there's a hierarchy in the Wilson coefficients. And also from unitarity, we can show that the weak gravity bound is satisfied. And in the case where the loop effects is coming from particles with charge to mass ratio that is not significantly bigger than 1, then there's no clear statement we could make. And similarly, characterizing the UV physics effects, we know that they are suppressed by the scale of lambda QFT, but there could be several types of lambda QFT, one associated with the open string, one associated with the closed strings. And if you do find a tower of higher spin states associated with a photon that is different from that associated with the graviton, you can again use unitarity to show that these two Wilson coefficients are positive. Okay? Now, one simple conclusion you can draw is that if loop effects dominate, and this is what we call case B1, when you find that the low energy spectrum below lambda QFT has states that have big charge to mass ratio, not only do we satisfy the weak gravity conjecture with this particle, an extremal black hole, a smaller extremal black hole can be the decay product of the large extremal black hole. So the mild form of the weak gravity conjecture is also satisfied. Okay? But this is not a particularly interesting case because you already satisfy the weak gravity conjecture with the particle themselves. We don't need to find other candidates for the extremal black hole to decay. Now, we are interested in whether an extremal black hole can play the role of the weak gravity state when you don't have such a particle. Okay? So in such cases, we note that the other effects would become dominant, whether other effects could be either effects coming from integrating out a neutral particle or from integrating out some stringy effects. Now, if you think about it, in general, if you stay away from the loop effects, it's not clear, at least from this table, that you can prove the mild form of the weak gravity conjecture by just unitarity alone. And that is because, you see, the unitarity constraint is on the two Wilson coefficients that do not involve the wild tensor. We only constrains alpha 1 and alpha 2. These are f to the fourth term and ff dual square terms. The terms that involve the wild tensor is not constrained by unitarity. So if that's the case, it would appear that we are stuck. We cannot really prove that the mild form of the weak gravity conjecture is even satisfied because the constraints depend on the Wilson coefficients that are not limited by unitarity. Okay? But as it turns out, this Wilson coefficient, even though it's not constrained severely by unitarity, is constrained by causality. So let's go through this argument in a little bit more detail. Okay? So as I mentioned, the higher derivative operators that involve the wild tensor would generate some helicity amplitude for photon-photon graviton that are not present in the original Einstein-Maxwell theory. Okay? So this higher derivative effects generate some additional amplitudes. And these amplitudes violate causality at an energy scale set by the Wilson coefficients. And so, in other words, from this argument, the effects at which alpha 3 is important would be classified into what we call the UV physics effects. Okay? The contributions from the neutral bosons would not give a significant contribution to alpha 3 because it violates causality. Okay? So the scale at which this causality violation should be at the scale above lambda QFT, but since the mass of the particle is below lambda QFT, they won't give significant contributions to this term. Okay. Now, so a way to see how causality is violated, it's a way to see how this causality violation happens is to consider a photon propagating in a shortwave gravitational background. So this is the argument given in the paper that I cited earlier. So consider a photon propagating in this shortwave background. Usually, there's a phase shift of the photon's propagation. This is a time delay effect, which is already present in general relativity. So in the presence of the interactions between the photons with the graviton, with gravity, there is a time delay as already present in general relativity, but the higher derivative operators involving the wild tensor would lead to an additional contributions to the phase shift of the photon's propagation. Okay? And this contributions to the phase shift is helicity dependent. And so if you have a photon with two helicity, one of this helicity mode would have a time advancement rather than a time delay, depending on the sign. So the one which has a positive sign would be a delay, but on the other hand, if it is a minus sign, it would be a time advancement. And this is a signal of causality violation. Okay? So this time advancement is a signal of causality violation. Now, it can be shown that if you have only massive particles with spin 2 or below, it cannot cure this causality violation. And this is because the phase shift generated by a spin j particle goes as s to the power j minus 1. And if you look at the time advancement due to these high derivative operators, it goes as s. So for massive particles in your theory with a spin strictly smaller than 2, would generate a term that is subdominant in the high energy limit. And so this would not be able to cure this time advancement. Now for particles with spin exactly equals to 2, this argument would tell you that the phase shift is of the same order as the time advancement. However, if you have a massive spin 2 particles, in the high energy limit, when S is very large, the mass of the particle is not very important. So you're again reduced to the same effect. So introducing massive spin 2 particles would still give rise to a phase shift in the same form as before, and you're not going to cure this time advancement. And in fact, you can show that if you have only a finite number of higher spin states, it's not going to help. And that is because causality and unitarity constrain the form of this phase shift. And causality would requires that if you have an incoming signal passing through this sharp wave, if the incoming signal vanishes at time smaller than 0, the outgoing signal should also vanish at time smaller than 0. And from that, you can deduce that this phase factor is analytic on the upper half plane. Okay? So this is a condition coming from causality. On the other hand, unitarity would imply that if you compare the amplitude of the incoming signal with the outgoing signal, the amplitude can only get smaller. And in other words, this would put a bound on the norm of this phase factor to be smaller than 1. It's bounded by 1. And this together would tell you that if you have a particle with spin, higher spin, if you have a finite number of them, it would still go not in the way that you want to cure this time advancement. But as we have seen before, when you sum over infinitely many higher spin states, the story could be very different. We have seen already in the scattering amplitude that if you sum over infinitely many higher spin effects, the scattering amplitude actually goes softer than you would have expected. If you take individual higher spin particles, it would give rise to effects that go stronger than s squared, but when you sum over the whole Regge tower, you get an amplitude that is softer, still satisfy the Froissart bound, strictly bounded by s squared. So the resolution to this problem of causality is that you have to introduce infinitely many higher spin states, and this is the effects of this. And this is what this higher dimensional operators tells you. When this higher dimensional operators becomes important, you would have to introduce not only one or a finite number of higher spin states, but infinitely many of them. Okay. So to summarize, this brings us to the two classes of theories that we consider. So now it should be clear why we have restricted ourselves to proving the weak gravity conjecture to the two classes of theories when we have control. The first class of theories are those when you have some neutral bosons whose mass is below the string scale. Okay? Having such a particles would tell you that their effects would be more dominant compared with the UV effects, because one operator goes like 1 over the mass of the particles square, and the other goes like 1 over the string scale square. So obviously the one coming from integrating out these neutral particles will be more dominant. And so if the tree-level effect is the dominant one, it would be the first class of theories that we consider, theories with light neutral bosons. Causality would imply that there is a hierarchy of the Wilson coefficients. the reason why alpha 3 is small is because this is an effect that violates causality, and so the bosons would not generate, the neutral bosons would not generate an operator with a significant value of alpha 3. And so we have seen that the weak gravity conjecture can be satisfied by an extremal black hole, by a smaller extremal black hole, if you can find in the low energy a parity even neutral scalar, or some spin particles with spin 2 or above, with a mass that is significantly below lambda QFT. And you can think of this as, say, the dilaton or some moduli that are stabilized by some mechanism with a value that is below lambda QFT. And if they are much, much smaller than lambda QFT, they would generate for us these higher derivative operators with the hierarchy that we want. And as a result, unitarity together with causality tells us that the smaller extremal black hole would be a candidate decay product. Now, there's a simple picture to understand why these neutral bosons can serve the purpose. Now, usually, when we think about the weak gravity conjecture, we thought about whether there are some there are some particles in the spectrum with a big charge to mass ratio. So this is, if you embed this picture into string theory, charged states are usually associated with open strings. Okay? So if your spectrum has some particles whose charge to mass ratio is big, you satisfy the weak gravity conjecture, then that's the end of the story. But suppose you don't find any particles with that we don't find any particles in your low energy spectrum, charged particles that satisfy the weak gravity conjecture. That means the charge to mass ratio Z is very small. Z is small. And so the charge to mass ratio, when it is small, means that we are in the limit when the string is very long. Right? So the mass of the string, the mass of this open string states is proportional to the distances between branes. And so a small charge to mass ratio, when Z is much more smaller than 1, means that the strings are very long. Okay? So in this limit, it is not so appropriate to think about the effect as loops of open strings. Rather, you should be thinking about the dual channel, where it is a tree-level exchange of Crow strings. So you can think of the neutral boson satisfying the weak gravity conjecture as the Crow string channel of what you normally call weak gravity particle, charged particles. It's not a charged particle because you are in a dual picture when an open string, tree-level open string picture is much more appropriate than loops of open strings. Okay, so this was case 1. Now, you can also prove that the weak gravity conjecture can be satisfied, even if you don't find such a light neutral scalar in your low energy, if you can find different towers of Reggie states. Okay? And as we argued before, if you have 2 different Reggie towers, one associated with graviton, Crow strings, and one associated with the photon, which is open strings, parametrically, the contributions from the open string Reggie tower will give a much bigger effect, because we are assuming we have a weakly coupled UV completion when the string coupling is small. And so the operators generated by the open string Reggie states would be a bigger effect than the operators generated by the Crow strings. Okay? So if you have 2 towers, then unitarity would imply that these 2 Wilson coefficients are positive. In making the argument, you can pretty much ignore the Crow string Reggie states at all and just make your argument purely with the open strings. And so the same type of argument can be made as before. However, not everything is completely lost. We know that the graviton has to come with a tower of Reggie states, even though the effects are supposed to be smaller compared with the open string Reggie states. And the mass scale associated with this Crow string Reggie states is determined by the Wilson coefficient alpha 3. And now, because the Crow string tower is parametrically weaker than the open string tower, you can already satisfy the weak gravity bound using unitarity argument. So in general, you include the contributions from the Crow string and the open strings Reggie states. We know that this is a subdominant effect, and the Wilson coefficients that does not involve the wild tensor is dominated by the contributions from the open strings. So this by itself is positive. So the weak gravity conjecture, the mild form of the weak gravity conjecture can be satisfied. In fact, if you have theories with supersymmetry, you can make even stronger statements. So this coefficients alpha 3 that characterize the high derivative operators involving the wild tensor is identically equal to 0 for theories with space-time supersymmetry. And that can be seen because the helicity amplitude that violate causality, the amplitude that I mentioned before, are incompatible with the Su-C-Watt identities. So either you have supersymmetry or not, you can show that the Wilson coefficients, the combination of the Wilson coefficients that determine whether black holes can decay into smaller ones, are satisfied. Okay? In supersymmetric cases, it's even better because they are, the coefficients that you know how to constrain is identically equal to 0. Okay. So how much time do I have? Maybe half an hour? 40 minutes? 20 minutes? Okay. So now I know the argument is a bit roundabout, but if you keep in mind a brief sketch at the beginning of the lecture, you will know how this goes. The fact that things look a bit messy is because I've tried to go over some of the argument in more details and closing some of the gaps. But this is a picture to keep in mind. So this summarizes the coverage of the argument based on unitarity and causality. What kind of theories would satisfy the weak gravity conjecture just with extremal black holes? So if the loop effects dominate, then you already satisfy the weak gravity conjecture in the first place, nothing to worry about. But we also see that you can satisfy the weak gravity conjecture with extremal black holes, so two types of candidates. But if you don't find the loop effects to dominate, then you would ask whether the tree-level contributions from neutral bosons dominate. And if yes, then you can use causality to show that the inequality that allow an extremal black hole to decay is satisfied. Now, if you don't find such a light particle in the spectrum, it depends on whether you have two types of Reggie towers. If you have only one type of towers, then you cannot make the argument. But if you have a Reggie towers associated with the open strings being dominant compared with the Reggie states associated with the closed strings, then you can use this to argue that the weak gravity conjecture is satisfied with an extremal black hole. The unknown would be the case when you don't have any light scalar below lambda QFT, and you have only one type of Reggie towers. This would be the case in the heterotic string if you also don't find a way to make the scalars lighter than the string scale. Suppose every scalar is of the order of the string scale, and in the case of the heterotic string, you have only one type of string excitations. You don't have a distinction between open and closed strings. So our proof will not apply to the heterotic string. Nonetheless, if you were to just compute scattering amplitude in the heterotic string, you can show that it is indeed still satisfied. So you can calculate some string scattering amplitude involving 4 photons in the heterotic theories, and you show that these two Wilson coefficients are positive, and the third Wilson coefficient is identically 0 because you have supersymmetries. Okay? Now, the fact that we cannot cover all possibilities with just unitarity and causality alone should not be a surprise to you. If you can prove the weak gravity conjecture just from few theoretical considerations, it should not be a Swampland condition. The whole point of the Swampland is that there are some consistency conditions that are not so visible from a pure low energy point of view. So we do, throughout this exercise, we do find that in some cases, it's not some magic UV physics that fixes the weak gravity bound, rather it just follows from simple few theoretical considerations. But in some other cases, they're not. And so we have to be somewhat more careful and clever in trying to prove how the weak gravity conjecture still holds in theories that are not covered by such cases, by such considerations. Now, I should also mention that in the earlier argument I made, that when you have space-time supersymmetry, you can show that the Wilson coefficients that are hard to prove that is bounded in one way or the other by unitarity is identically equal to 0. So you save a lot of work if you can show that alpha 3 is equal to 0. But this is an argument that requires only, that could be also in some cases be extendable to theories without space-time supersymmetry. And that is because in our arguments, we are looking at weakly coupled UV completion, so the tree-level effect would dominate. And so we are focusing on the tree-level scattering. And so some non-supersymmetric theories still inherit the same structure. The scattering amplitude still inherit the same structure as the supersymmetric theories. For example, there are non-supersymmetric theories that break space-time supersymmetry. But if you look at the tree-level vertices involving the bosonic sector, they still respect the same structure as the usual supersymmetric heterotic string. So for such cases, you can still argue that alpha 3, one of these Wilson coefficients that are hard to bound, would still be identically equal to 0. So all you have to do in such cases, even though they are not covered by this type of argument that I gave, you can still argue that one of the Wilson coefficients vanishes, and you only have to show that the other Wilson coefficients are positively bound. Okay. So let me make a brief comment about the relations of the weak gravity conjecture with black hole entropy. And the reason why I want to make this comment is that there has been a claim that you can prove the weak gravity conjecture based on considerations of an entropy of an extremal black hole. And this claim is based on the intuition that more degrees of freedom should increase the entropy. And so if you take this as an assumption that more degrees of freedom leads to more entropy, then integrating out some fields, some like fields, would generate these higher derivative operators and the results of integrating out these like fields should increase the entropy of the black hole. And now, at the same time, explicit calculation shows that the positivity of the entropy correction is equivalent to the positivity of the charge to mass ratio of an extremal black hole. So if you can combine this argument, namely that more degrees of freedom, namely the higher derivative operators always give a positive contributions to the entropy of an extremal black hole, and that it is equivalent to increasing the charge to mass ratio, then you are done, right? Because integrating out these effects increase the entropy. Increasing the entropy means increasing the charge to mass ratio. And that seems to be a lot easier argument than the one that I present here, okay? So the question is whether this intuition is correct, namely whether having more degrees of freedom always means more entropy. Is that always true that when you integrate out some degrees of freedom, the entropy of the black hole as a result would increase? Secondly, this seems to be a somewhat surprising relation. Why is the positivity of the entropy corrections related to the positivity of the extremal conditions, corrections? So when you increase the black hole's entropy, why do you also at the same time increase the charge to mass ratio of an extremal black hole, other than explicit calculations demonstrate that? Okay? So we would try to, we did try to answer these questions in the paper that we recently posted. So the first thing we wanted to emphasize is that having more degrees of freedom do not necessarily means more entropy. Okay? So here's a counterexample. Okay? So consider coupling a massive spin-2 field to your F squared term. Okay. So other than your Einstein-Maxwell theory, Lagrangian, you have some higher derivative corrections. In particular, there is a contributions coming from coupling a massive spin-2 field to F squared terms. So since the trace of the spin-2 field has no propagating mode, we can simply remove this interaction term by a simple Fourier definition. Okay, so this is a Fourier definition that does the job. It would eliminate this interaction term between the trace of the spin-2 field with F squared. And the resulting Lagrangian looks like this. Okay. Notice the sign of the F to the fourth term as a result. After you do the Fourier definition, it's negative. And as a result, if you compute the entropy of a black hole in the presence of these higher derivative corrections, you find that the black hole entropy is actually smaller than that of the Einstein-Maxwell theory due to the negative terms, negative coefficients of the f to the fourth term. So this means that having more degrees of freedom, in this case having a massive spin 2 degrees of freedom in addition to Einstein-Maxwell, does not increase the entropy of a black hole. So what's wrong with this simple argument that was presented in the paper? Well, as far as we know, the flaw in the argument is that it was assumed that the Lagrangian describing this system should reduce to the Einstein-Maxwell theory when you set the UV field, the massive fields, to 0 for any configurations of the metric and the gauge field configurations, any configurations of the metric and the gauge field. However, as you know, Lagrangian is not a concept that is invariant under field redefinition. So you cannot really make this statement that is not, this is not a physically meaningful statement to make, that the Lagrangian reduces to that of the Einstein-Maxwell theory. If you can make that statement, then the rest of the arguments hold. Fortunately, the argument that I presented to you, even though they are somewhat messy, and maybe to some of you may not be too illuminating, it's based on scattering amplitude, which is field redefinition invariant. So this would be an example that does not satisfy the unitarity bound, the counterexample that I gave, and so we would not run into the situations like this. Nonetheless, there's a simple argument we find that relates the positivity of the entropy corrections with the positivity of the corrections to the charge to mass ratio of an extremal black hole. And this is only true to some leading order, but sufficient for the purpose of our discussions. Okay? Now you could ask, what would be the type of corrections to the black hole entropy from these higher derivative corrections? Schematically, it has two contributions. So one contribution comes from higher derivative terms, just the presence of the higher derivative terms. When you compute the Ward entropy, they would contribute. And there's also a contribution from the fact that the higher derivative terms will shift the horizon. And the shift of the horizon would also contribute to the change in the entropy. Now, you can characterize the size of these effects. And depending on this Wilson coefficient alpha I, which are small, these are effects, these are numbers that are smaller than 1. This effect goes like square root of alpha I, and this effect goes like alpha I itself. And so this will be the dominant effect. So in the approximation to the leading order approximation, you can just simply look at whether the horizon shift contributions to the entropy is positive or not. And so for theories that satisfy unitarity bounds, we can show that this is indeed always positive. Okay? So the argument goes as follows. So you can calculate the entropy corrections coming from the higher derivative corrections, and in particular focusing on the effects of the shift in the horizon. And so you can see from this formula over here that as long as the shift of the horizon is positive, the entropy correction is positive. Okay? Now, in order for the entropy corrections to be well defined, the higher derivative corrections should work in such a way that the degeneracy between the inner and the outer horizon of an extremal black hole is resolved by including the higher derivative corrections. So an extremal black hole is one where the inner horizon and the outer horizon coincide, including the higher derivative corrections to split without introducing a naked singularity, as long as the theory is well behaved, satisfying the unitarity bound. And so since the outer horizon always increases when you split the inner and the outer horizons, the entropy correction, which is proportional to the shift of the horizon, should be always positive. So that's basically the argument. Now, in theories that do not satisfy the unitarity bound, it's not guaranteed that when you introduce the higher derivative corrections, the inner and the outer horizon, when you resolve it, would be free of naked singularities. So based on that, we can show that for an extremal black hole, the higher derivative corrections, the one that we study here for the purpose of the weak gravity conjecture, also guarantee that the entropy of a black hole increases in the presence of the higher derivative terms. In fact, you can show a bit more. Here I've sketched for you how the argument goes for an extremal black hole. You can show that for any charged black hole, and in fact for higher dimensional black hole as well, as long as the unitarity bound is satisfied, the entropy always increases. Okay. Okay, so I think this is a good place to sort of switch gear to the last topic that I want to briefly sketch for you today. I don't want to go into too much of the details because I just want to give you a feeling of what the unitarity and causality argument can say about stronger version of the weak gravity conjecture. Yeah. Now, I don't know about you, but I find it rather impressive that just based on unitarity and causality, you can already prove rather strong statements about the weak gravity conjecture, albeit the mild form. The question is whether the same kind of infrared consistency conditions can say something about stronger versions of the weak gravity conjecture. So in the first lecture, we mentioned that there are several stronger forms of the conjecture that requires infinitely many charge states. So one version is the sublattice weak gravity conjecture that requires that for a given charge lattice, you can always find a finite index sublattice in which at every site you would find a state that satisfies the weak gravity bound. Okay? So can we see something like this by looking only at unitarity and causality? Okay? So this is what we did in an earlier paper. So here we are interested in asking the question, suppose you are trying to see whether you find a weak gravity particles, right? Not necessarily the contributions from string, integrating out string states or neutral boson effects, but just from charged particles. Is there a way to link the weak gravity conjecture with some infrared constraints? And so the question that we ask is, starting from the Einstein-Maxwell theory with some additional charged particles, integrating out these charged particles would generate for us some higher dimension operators, just like what we've seen before. This would be a loop effect. And whether the conditions that we get by demanding positivity has anything to do with the weak gravity conjecture. Now, there's some similarity here. The Wilson coefficients that you generate from integrating out the charged particles depends on the charge and the mass ratio. In fact, earlier in the lecture, I showed you how they parametrically scale. With the charge to mass ratio, it goes like certain powers of z. And so if you were to write down an inequality involving these higher derivative terms, it would turn into an inequality that bound the charge to mass ratio. Would we be able to see something like the weak gravity bound strictly coming out from this analysis? So that's the questions. So to be more specific, let's say you start with Einstein-Maxwell and integrating all these charged particles, it would generate for us, again, these three terms. And positivity implies that some of these Wilson coefficients are bounded. And if you collect all the contributions from the charged particles, there are terms that goes like the couplings to the fourth. There are terms that goes like coupling to the square. Then there are also contributions that are irrespective of the coupling. So in particular, the contributions that are independent of the coupling would depend on some higher derivative corrections to gravity, higher derivative terms of gravity. And so schematically, the positivity bound coming out from integrating our charge fields would take this form. And this already looks very similar to the weak gravity conjecture if you were able to neglect the term that is independent of the charge to mass ratio that is sensitive to the UV physics. Okay? So that's the sort of argument that we want to make. This is by no means a proof. So from what I'm going to say now, there's a lot of there are a lot of assumptions that went in, but we wanted to see by making some assumptions about which term dominates, can we see features like the convex Howe conditions or maybe more from just unitarity. So let's take this positivity bound, for instance. You can make some statements if you are able to drop some contributions. In particular, if you are able to assume that this charge-independent contributions, which is UV sensitive, is negligible, then you get something which bound the charge to mass ratio from below. In particular, if you set this term to be identically equal to 0, you get precisely the weak gravity bound. Okay? So that's kind of interesting, although I cannot really say that this is a proof or anything close to a proof at all. However, if we were not able to drop these contributions that is independent of the charge, and if this term is the dominant, is a significant contribution, and in fact, if this is sufficiently positive, then the positivity bound would be trivially satisfied. Okay? So, for instance, if this effect is not negligible and if it's super positive, then we don't have any constraints on the charge to mass ratio of the particles that are integrated out. Now, this is by no means a proof or anything close to a proof of the weak gravity conjecture. Nonetheless, it gives you a different perspective on what the weak gravity conjecture means. It's a way to relate the weak gravity conjecture with the positivity bound and the fact that certain UV-sensitive contributions are negligible. Okay? Now, what could be quite interesting is if you repeat this argument, not only for a single U1, but multiple U1, can you find some stronger conditions, perhaps something like the convex Hall conditions that come out from unitarity and causality? That's what we did. And we find that not only do you find the convex Hall conditions, but something more. Okay? And the reason is the following. So you could bound the positivity by considering scattering amplitudes of the same photons. So photon 1 goes back to photon 1. But there are also some scattering amplitudes that involve different photons. So there are more bounds that you can write down. In particular, if you consider scattering amplitudes that involve different photons, the positivity bound takes this form, and it can only be satisfied if there are fields that are charged under both U1 gauge fields. If you have only particles that have only one type of charge, if there are no bifundamental fields, this inequality cannot be satisfied. Okay? So out of the many conditions you can write down based on positivity, you find that there must exist some bifundamental field in the low energy spectrum. And that should already ring a bell. So last time when we said that there's a Kaluza-Klein U1 in the game, things will become a lot more interesting because you can take one of this U1 here to be the Kaluza-Klein U1. So if you take one of the U1s to be the Kaluza-Klein U1, below the scale of the KK mode, you'll find that positivity bounds required the existence of these bifundamental fields. And so you could now vary the mass of this KK mode, namely the size of the compact dimensions, and you find that for a sufficiently small radius, the spectrum does not contain bifundamental field anymore. It carries a very tiny charge under the KKU1. And remember in the previous lecture, when we mentioned the sublattice weak gravity conjecture, that's precisely the regime of interest. When you look at small enough compactification, you find that the convex Hall is not satisfied. And so that motivates us to strengthen the conjecture to a sublattice form. Here, again, the same thing happened. When you look at Kaluza-Klein reduction, the fact that you have bifundamental fields, the fact that unitarity implies bifundamental fields, and for sufficiently small Kaluza-Klein, for sufficiently small compact radius, the bifundamental field does not contribute. And so that would mean that we have to strengthen the weak gravity conjecture as well, based on the simple unitarity argument. So again, a way to make the theory healthy again is to introduce a tower of the tower of charge states under the original U1. So not only do you have a state that satisfies the weak gravity conjecture, if you have a tower of particles that are charged under the U1, when you Kaluza-Klein reduce, for any radius of the compactification, you'll find that there are still bifundamentals. Okay. This will not be the case if you have just a single states charged under the original U1. If you have a whole tower of states, then it gives rise to bifundamental fields for any values of the KK radius. Okay? So this suggests that the weak gravity conjecture has to be strengthened somewhat in the presence of a KK U1. And this is what we call the tower weak gravity conjecture. Namely, you will need not only a state that satisfies the weak gravity bound, you need infinitely many charged states. And the presence of the infinitely many charged states is to collectively give a big enough contributions to the positivity bound, which requires the presence of the bifundamental fields. And so it's kind of interesting. I mean, the argument is completely sort of orthogonal to the one that I gave previously. Still, in both cases, you find that consistency among KK reductions requires some stronger conditions. And here we see that we need a stronger conditions in the sense that there's a tower of states. The tower of states do not have to be evenly spaced. They do not even need to fill the full charge lattice or sublattice at all. All they need to do is to collectively give big enough contributions to the positivity condition, no matter how small the compactification radius is. Okay? So this is what we call the tower weak gravity conjecture. So to summarize the lecture today, we have seen that the mild form of the weak gravity conjecture can be shown following constraints from unitarity and causality, at least for a wide class of theories that can be naturally realized in string theory. So we have identified theories in which our proof would apply, theories where we have like neutral scalars, such as dilaton or other moduli that are stabilized below the string scale. Or when you have open string type UV completion, you can show that a large extremal black hole can decay to a smaller extremal black hole. And we have also seen that the higher derivative corrections to the effective actions of photons and gravitons would correct the black hole entropy and make it more positive. And now we have seen throughout the discussions that having more degrees of freedoms do not mean more entropy. So we cannot use the fact that entropy correction is positive to show the weak gravity conjecture. But this is a consequence based on unitarity. So if you have theories that satisfy the unitarity bound, you have the charge to mass ratio corrections bigger than 1. And at the same time, you can show that the entropy corrections will be positive. Now, in this lecture, I have only focused on black holes in 4 dimensions with only a single U1. The analysis that I did is the minimal. So you could upgrade the analysis to including additional scalar degrees of freedom in the effective action if there's some master scalar field as well. But in our work, we also extended the analysis to higher dimensions and to multiple U1s. The story is pretty much straightforward. Now, in the first lecture, I mentioned that the weak gravity conjecture usually was stated in the form of the charge to mass ratio of particles. And this is the one-form versions of the weak gravity conjecture. And it can be applied, the weak gravity conjecture is more general. It can be applied to p-form fields, as well as objects that are charged under them, namely the branes. And so when you refine the weak gravity conjecture to a strict inequality, when you have particles that have charge to mass ratio strictly bigger than the extremal value, when you generalize it to branes, you can use it to argue that non-supersymmetric ADS vacuum are unstable. We will mention this connection in the lecture tomorrow. Now, the reason why I bring this up before we talk about it tomorrow is that, interestingly, the decay channel of an extremal black hole that we find may have some bearings about this conjecture. Because the near horizon limit of an extremal black hole is an ADS2, the fact that we find that an extremal black hole can decay also suggests that perhaps the non-supersymmetric ADS vacuum would also have a decay channel. Okay. In the lecture tomorrow, 2 lectures tomorrow, we will discuss applications of the Swampland conjectures to particle physics and cosmology. We will see how the weak gravity conjecture and the Swampland distance conjecture can be used to constrain the amplitude of gravitational wave generated in some models of inflation. And we'll also see what the Swampland conjectures say about the QCD axion, dark energy, and neutrinos. So this is a good place to stop. And I would like to thank you for the attention.
Thank you very much. In the previous slide, so we made a statement that like previous slide. So that generalization of weak gravity conjecture means that like non-supersymmetric ADS vacuum is unstable. So in the classical theory, is it like ADS non-supersymmetric ADS space, is it stable under any nonlinear perturbation?
So so the instability that I'm mentioning here is a vacuum transition. So there are other forms of instability too. So to answer your questions, I'm only focusing on the vacuum transition instability, and that would be the subject for tomorrow. But you can also study all kinds of perturbations around the background to see whether there is instability as well. So in the lecture tomorrow, you'll see something with much lower energy that you can tunnel to.
So I have two questions. One is, you mentioned the validity of the four derivative analysis, right? So I think there's some lower bound of the scale that is valid. So it's a logical, I think it's a logical possibility that the external black holes decays down to that scale, and there's a lot of black holes lower than that scale. And is that okay physically, or you think it's unlikely that such kind of thing happens?
So what scale do you have in mind?
The full derivative analysis has some scale in the denominator, and that scale, I have that scale.
So for us, it would be a tunable parameter because we can consider as big a black hole as we want. Right? So this is set by the charge or the mass of the black hole. So if your approximation is not good, you make the black hole bigger, and so you can ignore the higher derivative corrections. So imagine you can make the black hole as big as you like and consider only the leading corrections. That's the assumption.
So my question is, like, if there's a scale of validity of that analysis, under that scale, you have infinitely many state of black holes, right? It's possible. So so usually weak gravity conjecture analysis argument says, like, if you have infinitely many states, then there's a contradiction or something, right? Yeah. So is it okay in your analysis? I mean,
so here, as long as you can show that there's a finite mass black hole in which this happens, so as long as you break the chain at some point, that would be okay. So the argument I made earlier was that if you don't have a weak decay channel for the black hole, you can just have your thought experiments with as big a bound state as you like, with infinitely big mass and charge, and it doesn't, no matter how big it gets, it never finds a decay channel. Here we find that for sufficiently large black hole, it would already decay, so it could not, you cannot extrapolate all the way forever.
Thank you. Another question is, you showed the weak gravity conjecture for a class of theory, right? And is there any explicit counterexample for that is unitary, causal, and violates the WGC, or is it possible that the whole theory respects the WGC?
Yeah, so we haven't found any counterexample to the weak gravity conjecture. So there are examples that fall outside the regime of validity for us, like the hadrotic string would be an example, but the hadrotic string satisfies the weak gravity conjecture nonetheless. And so it would be interesting if one finds a counterexample, but I don't know of any at the moment.
Thank you.
Okay, there's a question.
So this question is a bit orthogonal to what you've been presenting to us. Mm-hmm. And on the time delay argument, so you have mentioned that you can only conclude that if we have higher spin states, then we should have the whole rigid tower. And does the argument give any bounds on the slope of the rigid tower?
So the Reggie slope is set by the Wilson coefficients. So you can literally think of the scale at which the causality is violated to be your string scale. So the scale that I call m Planck divided by root alpha 3, that's the scale when your causality breaks down. So you have to replace it by something which is not ordinary QFT, but something stringy. So that is your string scale. So implicitly somewhere in the PowerPoint, I already set it to be the string scale. But
thanks.
Hello, I have a very naive question. Mm-hmm. You mentioned in the mild form of weak gravity conjecture that you need, in some specific example, a light neutral boson, right?
Yeah.
Why do you need that for? Are you imagining like a scattering amplitude in which this boson dominates over the graviton exchange, something like that?
Yeah. So if I can prove it very generally, I don't have to bring in this extra scalar. So the difficulty is because if you don't make any assumptions, the scattering amplitude involving the graviton extreme will dominate. So you want some other effects to dominate in order to prove the positivity bound. And so we come up with these two classes of theories, one in which there's a neutral bosons which give a more dominant contributions to the operators. And another possibility is to have just different towers. But it's not completely unreasonable because if you look at the string compactifications, you don't want all your moduli field to be of the order of the string scale. You actually, most of the time when we look at the string back here, we are assuming that the moduli are lighter than the string scale, and we actually stabilize them within the low energy effective field theory.
This is supposed to be valid also in the context of ADS-CFT, or do you have a specific context in mind?
So here, we are considering finite Planck scale. So, the four-dimensional Planck scale is finite. So we are compactifying the internal space.
Okay. Okay. Thank you.
Yeah.
Okay.
Actually, I have a simple question, and in weak gravity conjecture, we express the higher derivative of stress tensor for matter, F mu nu.
Can you say it one more time?
I mean, maybe in first or second slide of weak gravity conjecture, we express the higher derivative terms for F mu nu and some coefficients, and but in the application to black hole entropy, we express the higher derivatives of the metric. So I wonder that why do we express the higher derivatives of metric, not stress tensor, just?
So are you asking why these are the only higher derivative terms up to 4 derivative order?
My question is just simple. This section is expressed to higher derivative of F mu nu. Yeah, but in the application to black hole entropy, when we can get entropy, we express the higher derivative of the metric, not F mu nu. So
So a lot of these terms are related by free redefinition. So this is just one basis in which I write down things. So you can rewrite it using equation motion and express the F in terms of the curvature.
Okay.
Maybe we can postpone these questions to the Q&A session. So let's thank the speaker.